Okay. Kalau tak ada, next we are going to
Sir,
look. Yeah.
Sir, kenapa M dot boiler tu equal dengan M dot, sir?
That is being, you read the question.
Oh, okay, sir.
You read the question. It's being the
Stated.
question stated that is the boiler mass flow rate.
Oh, okay, sir. Sorry, sir.
Okay.
Okay, thank you, sir.
Tak apa. You don't understand, you ask me. Maybe kadang-kadang kita miss some very important data, then we have to look back to the question. Kalau case macam ni kan, dia kata 22, right? They steam through the boiler. And that is our total mass of the whole cycle.
Okay, sir. Noted.
All right. Okay, now we go for the, as I mentioned before, we do have the second type of our feed water heater, which is the closed type. The function is the same. The integration or the application of our feed water heater is purposely to increase the thermal efficiency. Okay, to increase the thermal efficiency. So again, the schematic diagram, this is your schematic diagram. This is our turbine. Let's say we are going to incorporate only one closed type of feed water heater. Then we are going to bleed at this point. Okay, I should remind you all, if I say bleed, this is equal to the extracted, okay? It's equal to the extracted steam. Okay? This is bled steam or the extracted steam from the turbine. So this is our turbine. This is where we extract some of the steam to be flow to a feed water heater. Okay? Of course, we have our boiler right here and our superheater. This is the site for the, this is our superheater. Okay? And of course, before going into the boiler, we are going to have one pump. This is our feed water pump. This is our turbine, this is our superheater and also the boiler. Okay, this is the boiler and also the superheater part component. Then output from the turbine, let's say that we are going to run or to drive a electrical generator. So what is being bled here is, let's say, is Y. And of course, when we have a closed type of feed water heater, the bled steam and the feed water does not mix. Okay, does not mix. So of course, this is from the condenser side. So this is our condenser. Outlet from the turbine going into the condenser. It's going to condense. And then we are going to flow through this feed water heater. And if we look right here, let me see again my diagram. Am I right? Oh, no. The feed water heater is not right here. The feed water heater should be after the condenser. Let me correct that. Okay, it should be our feed water heater. Okay, after pumping process, then only we go to the feed water heater. Sorry, this is feed water pump. This is feed water pump. So this is our feed water heater. Okay. Of course, for a closed type of feed water heater, we have 2 inlet and 2 outlet. Right? Okay, that's right. And then what happened to this steam? The steam coming out, the blended steam coming out from the feed water heater, we are going to flow in to the condenser. Okay? And in the condenser, right, if we compare this pressure and this pressure of condenser, the condenser pressure is lower than the blended steam. Why? So if we want to mix with the condenser, we must have the same pressure. So this is higher than this pressure. You see, this is pressure, this pressure is higher than this pressure, which is the condenser pressure. And then this feed water pump is going to increase the pressure to the boiler pressure. Okay, so this is our path from the feed water heater. And now we need to change the pressure of at Y to become the pressure of the condenser, so that this mixing of this blended steam, which the energy has been absorbed by the feed water heater, feed water will be mixed with the condensate from the turbine. So meaning that we must have a what we call as the throttling process. This is the throttling process. Okay. So this complete our cycle. Again, from state 1, we have blended steam at state 2, and from this point, the balance of the steam will be 1 minus Y will be expanded furthermore in our turbine. Then this 1 minus Y will be flow into the condenser to be condensed to liquid form. And also, we are going to mix the condensate from this feed water heater after the throttling from the pressure of Y, which is at P2, becoming the pressure the same as the condenser pressure. Okay, then only we are going to pump in, increase the pressure to the pressure of the boiler and superheater. Right? So if this is 1, this is true, 2, then we assume this is 3, this is 4, so this is 5. Okay. So next one, what are we going to get the number of this? Maybe we get it 6 after the water heater. And from 2, maybe we go to 7. And from 7, we go to 8. Okay. That is the schematic diagram. This is a turbine. This is turbine at the first stage. Turbine at the second stage.
Condenser
Ya.
daripada water heater tu ke boiler tak ada pump ke?
Macam mana?
Daripada yang feed water heater ke boiler kena ada pump ke?
Tak, saya tak apa jelas dengar Amirul. Repeat again Amirul, tak apa jelas. Terputus. Anybody get what is Amirul asking? Amirul, okay.
Test. Daripada feed water heater tu ke boiler
Okay. Yeah.
kena ada pump ke sir?
Kenapa kena ada pump?
Nak naikkan pressure dia
This one?
daripada feed water heater.
Yeah, this one. Tengok The feed water heater, alright, from the condenser, we pump at the feed water heater to the pressure of boiler. Okay? This is the beauty of those type of feed water heater. We don't need extra feed water pump.
Okay, thank you sir.
Okay, if we have one feed water pump closed tight, we only need one feed water heater. It's not like it's not like the open type of feed water heater. The open type of feed water heater, it must operate in between two pump. Okay? This is the advantage of closed type of feed water heater. We have reduced the component, but we are going to add up only a throttle valve. Okay, this is the throttle valve. Okay. So if we look at the TS diagram, TS diagram, okay. So how many pressure that we are going to sketch? The highest pressure, this is the boiler pressure, correct? The lowest pressure is our condenser pressure. And the intermediate pressure should be our pressure of the blended steam. Okay, the extracted steam. So from here, we are going to have our first expansion from 1 to 2, and our second expansion from 2 to 3. Okay, let us look whether are we using the same numbering. Okay, this is 1 to 2. At point 2, we extract or we blend some of the steam. The rest is going to be 3. Okay, so this is 1, 2, 3. From 3, what is happening from 3? From 3 is going to condense to be 4. Okay, so now from 3 going to be 4. And if this is our pressure of the boiler, okay, after 4, what we could find 4 to 5. The pumping process from pressure 4, we are going to increase to pressure 5, which is equal to pressure 6, and which is equal to the pressure of the boiler. You see, 6 is equal to the boiler and superheater pressure. So from 4 to 5, this is from 4 to 5. Okay, and then after that, from 5 to 6. This is the tricky part. Okay, now from 5 to 6, what we are going to have, we are going to have the increment of temperature because of this feed water heater. the feed water will be heated by the extracted steam. You see here? From 5 to 6, the feed water from 5 will absorb the heat from the Y, which is at 2. So it will absorb until becoming 6. Okay, until becoming 6. So 5 becoming 6. And how are you going to plot the 6? You are going to plot the point 6 is horizontally the same as the feed water heater temperature. This one. Okay, you are going to put it as horizontal, the same level of the horizontal of the T set at this temperature. And because we are assuming that all the heat produced or available from the Y will be absorbed to increase the temperature from 5 to 6. So now we can highlight the process from 5 to 6. From 5 to 6 is the increment of temperature due to the where is my black color? Okay. That is the 6 to 5. And then from 6 to 1. You see, where is 6 to 1? The 6 to 1 is the heat absorbed by the water at the boiler and superheater. 6 to 1. Therefore, highlight the 6 to 1. Okay, so this is our arrow. And we have one more process, which is the throttling process from 7 to 8. What is 7? 7 is the saturated temperature or the condition of the Y steam, which is coming out from the feed water heater. And we assume that what is coming out right here is as saturated liquid at the pressure of 2. Okay? And pressure of 2 is equal to the pressure of 7 because we know this is the same line. Okay, this is the same line. So the pressure 7 and pressure 2 is the same. So this is 7. So this is the process whereby we extract the heat. Initially, from 2 to saturated vapor, we are going to extract in terms of the sensible heat. But from this saturated liquid, saturated vapor up to 7, we are going to extract in terms of latent heat, whereby we have the condensation or the phase change from saturated vapor up to the saturated liquid. And then from 7 to 8, from 7 to 8 is a throttling process, whereby we know that for a throttling process, we know that from our thermodynamic, the H7 should be equal to the H8. Okay, H8. Let me put in the better handwriting. Sorry guys, this is H7 is equal to H8. And this H7 equal to H8, which is assuming that is a throttling process. This is a highly type of expansion process which is not reversible. And we don't know what's actually the path taken by this process from 7 to 8. We don't know what is actually happening. But for sure, the enthalpy is the same. Therefore, to represent this type of process, we are going to put this dotted line from 7 to the pressure of condenser. You see, at the 8 is the pressure of the condenser. So this is the process whereby we have, this is 8, where the 8 is the point where we mix the condensate from the turbine and condensate from the feed water heater. Okay, we mix it together. So at the pressure of 8. Okay, all the enthalpy 1, 2, 3, 4, 5, we are going to get it as what we have done before. Alright, I repeat again. Enthalpy 1, H1 is based on P1, E1. Enthalpy 2 is based on P2 and S2. Enthalpy 3 is based on P3 and also enthalpy 3. H4 is equal to HF at P4. And then H5 is equal to H4 plus P5 minus P4. If this is the flow rate of 1, this is what we are going to have Y flowing into the feed water heater. The balance right here, how about 3? Can you see the 3? This is 3 coming in plus the Y. Okay, remember from here we have 1 minus Y. Right here we have Y. Okay, this Y, Y, Y. So what is coming out from 4 is 1 again. Okay, it's 1 again. So beginning at 3, you see 3, coming out at 4. So in the condenser, we are going to have, coming out from the condenser, we are going to have 1 again. Okay, 1 again. So beginning campur-campur 1. Dia campur dekat sini 3. So at the condenser, the flow rate should be, what do you think? It should be 1 or 1 minus Y in the condenser? Right here. For sure, 4 is 1. So if we are going to calculate what is the heat at the condenser, right? What are you going to do? Anyone? So we need to calculate the energy balance at the condenser side, which is the H3 multiplied by 1 minus Y plus H8 multiplied by Y equal to H4. Okay? If the question asks for the energy balance of the condenser. But right now, as far as what we are going to solve for the quality, for the SSC, for the thermal efficiency, I think we don't need anything, any energy balance at the condenser side, because the H4 and H3 we are determining by using this method. This is H4, this is H3. Okay? And what is H6? And the H6, we are going to get it as equal to H7, which is equal to H8, and this is equal to HF at the pressure of 2, or also the same pressure as 7. Okay, so I should put right here, better putting right here at 7, HF at 0.7. Although we know that the pressure of 7 and 2, they are the same. And there's one final parameter that we must have it. What is it? After getting all the enthalpy, what's next? You're going to get. What do you think?
Y.
Y. So looking at the feed water heater, by using the energy balance of the SFEE, steady flow energy equation, then the energy in is equal to the energy out. What is the energy in? This part, energy in, which is Y H2, this is our energy in, plus what is flowing right here is 1 H5 equal to the energy out Y H7. Okay, Y H7, energy out, this is 1 H6. So remember that H2, we have solved it. H5, we got it. H7 equal to HF, and H6 equal to H7. Okay, H6 equal to H7. Then, after putting all the enthalpy, then we could solve for the Y. Okay? So, what you are going to do, I would suggest you to find out more about the open feed water heater. We have open feed water heater, and also we have closed feed water heater. So what I want you to look for is to see the differences between these two, because this is a very, very famous question for part 1 for the steam cycle. Right? Name 3 differences, or name 2 differences between the open feed water heater and the closed feed water heater. You may discuss it in terms of the operational, okay. You may discuss it, the operational, individually. You may discuss it, the installation in the schematic diagram. And you may discuss it in terms of the component. Okay, like I have said before this, if an open feed water heater, it must work in between 2 pumps. For closed type feed water heater, we only need 1 pump, but we need an extra component, which is the throttle valve. And you may discuss on the throttle valve itself, why we need the throttle valve. Okay, so you might look the differences in terms of this aspect. One is operational, one is direct mixing, another one is indirect mixing. The installation schematic diagram, where do we install that? how do we install it, and the component you may discuss the extra component that we need for the open type feed water heater and also for the closed type feed water heater. And the last one is you may discuss in terms of the which one is more simple. Okay, which one is more simple? That's the simplicity. Simplicity. Okay, the simplicity. Which is more simple? Which one is more, maybe in terms of maintenance also you can touch on it. Okay. So any question, guys? Two questions. Let us look one example of this usage of feed water heater, the closed type. Which is I take this question from the Yunus Chenge textbook. Okay. Oh yeah, I forgot to discuss about the flow rate. So of course the flow rate is basically based on the Y value. Okay. Oh, the flow rate is already here. Okay. Just need to recap back. The flow rate from this point to this point, from this point to this point is 1. From this point to this point is 1 minus y. In the condenser is 1 minus y. Okay, and from this point to this point is already mixed. This is 1, and the rest is 1. From here to here, this is 1. So as far as the flow rate is concerned, there is the fraction flowing in each component. That will be taken care when we calculate the work and also the work net, the work on the turbine, and etc. Okay, let us look lead together this question. Consider a steam power plant that operates on the ideal regenerative Rankine cycle with a closed feed water heater. The plant maintains the turbine inlet at 300 kPa and 350 degrees C and operates the condenser at 20 kPa. Steam is extracted or bleed at 1000 kPa to serve the closed feed water heater, which discharges into the condenser after being throttled to the condenser pressure. Calculate the work produced by the turbine, the work consumed by the pump, and the heat supply in the boiler for this cycle per unit of boiler flow rate. Right? So we are assuming that what is flowing in the boiler is 1. Okay? The flow rate is 1. Also determine the plant thermal efficiency and the specific steam consumption. Okay? The plant that we are going to discuss here is the same what I have sketched in the schematic diagram. So what I'm going to sketch here is only the TS diagram. This is the TS diagram. Right? 300 kPa and 350. The first pressure is the boiler pressure. Let's assume this is the boiler pressure. And given right here 350, this is 373, so 350 a bit lower. So this is 350 degrees C, and the pressure is 3 megapascal for the boiler. Right? And then we have the condenser pressure is at 20 kPa. Let's say this is our pressure of the condenser, which is 20 kPa. And we have extracted steam at 1000 kPa. So we don't know whether this pressure of 1000 will give us the end of the first stage of expansion as mixture or still superheated vapor. So of course we need to prove it. So this is the pressure of 1000 kPa. But we must sketch something first. So I'm going to sketch this type of sketching. Then what I can put right here, the expansion process, is to that what we are looking, the end of the first stage expansion, it's still at superheated vapor. But need to be proof what is exactly or what is the actual condition of point 2. Okay, so this is point 1, this is state 2, this is state 3, and we know that we are taking we bled some portion of the steam at pressure P2. And then if we could project our pressure, this is our pressure. And if we look in terms of the pumping process, let me adjust this a bit. Oh, sorry. Let me adjust this a bit. Same goes for this. So I need to put this line a bit lower, a bit steeper. Okay, let's say this is our, all right. So this is the pumping process. Sorry guys, I couldn't control my hand. Look very crooked. Okay. And this is the bladed extracted steam. And this is our throttling process. This is our condensation process. So this is 3 to 4, 4 to 5, and then 5 to 6. And then this is 7, and this is 8. So this is the arrow. This is another arrow. Oh no, put the arrow here in the middle. Represent the process in the boiler and superheater. 5 to 6, another process in the feed water heater. Okay? So that is how it look on the TS diagram, but yet we need to know what is 2 and 3. Okay, 2 and 3. So now let us prove 2 and 3. Okay, so what we need, we try to prove or try to get the enthalpy of state 1. So based on what? Based on the P1, which is equal to 3000 kPa, and T1 is equal to 350 degrees C. So what state is that? If you look at 3000 kPa from our
Superheated.
superheated, why is
Yeah.
it superheated?
Because at 3000 megapascal, the temperature is 233 is the saturated temperature.
Okay, so this is what you get for the T-set at 3 megapascal, 233. Okay, therefore, we are looking at the T1 is greater than the T-set at this value. Therefore, superheated vapor. So can we get our H1 right now?
Six point seven four five zero.
Pardon?
6.7450.
Enthalpy.
Yes.
How come enthalpy 6 point? Enthalpy. Not
Oh, sorry.
no, enthalpy.
Oh, sorry, sir. 3116.1.
3116.1.
Yeah.
Then only we get the entropy, because we need that, because S1 is equal to S2. 6 point what is now? 6.7?
7450, sir.
7450.
Yeah.
Okay, thank you. And then we get our H2, but before that we need to know what the state of 2. Right? We need to know the state of 2. So what is the state of 2? We look the SG at 1000. Okay, SG is 1000. So what do you get?
Higher than SG.
It's still superheated vapor. Okay, so P2, based on P2, which is equal to 1000 kPa, and based on the S2 is equal to S1, then we are going to have the S2 is greater than the SG, correct? Greater or smaller?
Greater.
Greater. The S2 is greater than the SG2. Therefore, superheated vapor. So this is our value of 6754. So if we look at 1000, 1 megapascal, 1 megapascal, this is 1 megapascal, and our entropy is 6.74. 6.74. Yeah, this one. This and this. This will correspond the enthalpy of here. So you have to interpolate. Okay, you have to interpolate. So by interpolation, try to get that. We will have our H2. Okay, how much that? Got it?
28,
28,
52,
52,
0.86,
point
86.
9. Okay. Oh, guna which table ni?
Separated paper. Table.
Everybody agree? 2852.9?
Agree, sir.
Okay, thank you. And then after that, we are going to look for the H3. But before that, we need to get what is the state of 3. So based on the P3, which is equal to the pressure of 20 kPa, and based on the S3, which is equal to the S1, so what we have in terms of the entropy right here is 6.6450. I think it should be mixture, right?
Mixture.
Okay, so meaning that we are going to have the S3 is less than the SG at 3, therefore mixture. Then once you have your mixture, then get your X value first, the X3, because we need to get the H3. Because H3, we must use the formula involving the X3. So you must get your X3 first. The X3 is equal to S3 minus SF3 divided by SFG3. Will you please get what is the X value?
Zero point 0.8357.
Okay, 0.8357. Then get your H3 using the formula of HF3 plus X3 HFG3. Okay, what's that?
So I got 2221.58.
All right. Next, after 3, H4, which is equal to HF at 20 kPa. Equal to
251.42.
251 0.42.
42.
42. All right. After H4, we need our H5. What is H5? H5 is equal to H4 plus 0.001. The maximum pressure is 3000. Sorry, I put the formula only. This is your P2. Sorry, not P2. P5. Okay, P5 minus P4. Where your P5 is 3000 MPa and your P4 is equivalent to the condenser pressure, which is 20 kPa.
Two five 4.4.
Okay, 254.4. Right, so it's very small, right? The work of this is very small. Okay. After that, we are going to have the H6, where the H6 is equal to the H7 equal to the H8, which is equal to the HF at our intermediate pressure, which is at 1000 kPa.
Seven six 2.51.
Pardon?
762.51.
Okay, thank you. Everybody agree? Everybody
Yes, sir.
agree? Okay,
Yes, sir.
good. So now we have all the enthalpy. What's next? Get your Y value. Okay, get your Y value by looking at the SSEE, SFEE of the feed water heater. That is what we have written just now. Where is it? Oh, not right here. Remember the formula? Okay, just to sketch it back to have a very clear picture. So this is our feed water heater. This is our state 2 Y. This is our state inlet. After the pump. So after the pump, what is the state after the pump? 5, right? So this is 5 and the fraction is 1. After 5, it's 6. From 2 to, remember, what is the numbering we use after 2? 7, right? Correct?
Yes, sir.
This is Y. So energy in H5 times 1 plus H2 equal to the energy out. Okay? From this energy balance, you will get the Y value. So after that, you can get all the parameters and make sure that you have this answer. The first answer is the thermal, the first answer is the work, calculate the work produced by the turbine, which is H1 minus H2 plus W23, where the W23, remember, this is the fraction of 1 minus y. So what is W23? 1 minus y, H2 minus H3. So you get this value. Okay, after that, get your thermal efficiency. Where is your thermal efficiency? No. Also determine the plant efficiency. What is your plant efficiency? Right here is giving us 3.0 kilojoule per kilogram. Wow, what is number is that? Seven for one should be your W net, W turbine, or your that is your W for the pump. 741 is your work of the turbine. And then your thermal efficiency is you will get around 31. Okay, your thermal efficiency you will get around 31%. Okay, so have a try, guys, and maybe you can look tomorrow, not tomorrow, on Wednesday. We can have a look again, and on Wednesday, I'm going to look at one question from past year's test or exam. Okay? So guys, let me take your attendance first. So I put in chat for everyone. Control V. So that is your